I have a very unusual medical practice, which, it's a very nonlinear path that it took to get me here. But one of the best parts about it is I don't actually spend a whole lot of time treating patients, which is not to say that treating patients isn't fun, but it's that you have more time to think. And one of the greatest complaints I hear from most physicians that I meet is, gosh, I love what you're doing, but like, how do you have the time to learn all of the new material? Because as you'll see in a moment, everything that I'm going to talk about today, is completely new to me since my residency, which is over 10 years ago. So I really did have to learn everything from scratch through mentorship, reading, all sorts of things. Well, none of that would be possible if I didn't have analysts who work for me. And one of them is here today, Bob Kaplan in the front row. So Bob is actually two are here, right? Megan's right here, sorry. But really, it's these analysts who just kind of enable this practice and this approach that we're going to talk about to sort of exist, because you have to be constantly surveying the literature. You have to constantly be, try to assimilate and make sense of things that don't seem to make sense. So anyway, I think the real joy of what I do now is that I basically get to learn all the time. So hopefully I'll share a part of that today. So before I begin, I will also share the motivation for this, because I, as David said, trained in general surgery and surgical oncology, which really doesn't directly lend itself to what I'm doing today. But I think there are kind of two things that I've experienced in my life, which I'm sure many people in this room can also relate to, that probably got me where I am. So the first was, I was always drawn to oncology patients. So when I went to medical school, I assumed I would be a pediatric oncologist. I ended up not doing that, but I still wound up in oncology through another channel. And when I was at the NIH, as David said, I worked in the lab of a guy named Steve Rosenberg, who's an immunologist doing immunotherapy for cancer. But I always found myself attracted to the types of people who took care of cancer patients. And part of that was just learning to be around people who were dying, because as anybody here knows and I can see people that I know who work in cancer, unfortunately still many of the patients you take care of die. So Steve Rosenberg gave me really amazing advice as a medical student, which was, most physicians tend to retreat from dying patients, but you should actually go to them. So it's very easy to be there high-fiving the patient when they have a great outcome. It's much harder to be there when you fail. And I embraced that advice, and I found it to be one of the most rewarding experiences of my life, because you really learn about life when you're with people who are dying. People are much more open and honest, and I think there were a number of lessons I took from that, but certainly one of them was that life is finite, which, again, there's nobody in this room that doesn't know that, right? But it's one thing to know it intellectually versus to know it sort of viscerally and emotionally. And so I think there was always this sense with me that when it's over, it's over. Cancer, and by extension most disease, doesn't particularly discriminate by, who you are, how smart you are, how rich you are, how successful you've been, how nice you are. Those things didn't seem to matter that much. It was just sort of bad luck, like these bad things happened. Unrelated to that, and separated by many years, the second event that sort of catalyzed this interest in me was the birth of my daughter. Again, probably anybody in this room who has a kid feels the same way, but for me, it definitely changed the focus from only my own performance, which at the time was really the only thing I cared about, to, frankly, living longer and less concerned with performance. In fact, today I would argue the pendulum has swung so far the other way, I pretty much can't perform at anything anymore, and it doesn't seem to bother me that much. But nevertheless, those two things have catalyzed where I am. So I want to talk to you about three things today that are all centered around longevity, but the way I'm going to present it is probably going to be a unique way. And I think, actually, we were having dinner one day, David, when I sort of sketched this out over a napkin, and that's sort of when you said, you should really just come and give this talk, because it's kind of it's a unique way to think about the problem. A guy named Dennis Calabrese, who's someone I consider a mentor, really schooled in me a philosophy many years ago, which was that in life, if you're trying to solve a problem, always go through the following chain in order: objective, strategy, tactics. It didn't make a lot of sense at the time, but as my life has gone on, it has made more and more sense. Now, most people understand what the objective is. That's what you're trying to do. Many people understand what tactical levers are. What are the actual things that you can control to exact the outcome. But where I think most people are a little foggy tends to be on strategy. And so the talk I'm going to give today walks through the objective, the strategy, and the tactics of sort of a clinician's approach to longevity. Before I begin, I will explain exactly using one of my favorite examples. Actually, Bob reminded me of this example a few months ago. I used to box growing up, so boxing and boxing history has always been near and dear to me. So anybody in this room even old enough to remember who Muhammad Ali is and George Foreman? A couple of you? All right. So Muhammad Ali, of course, was by some estimates the greatest heavyweight that ever lived. But on a couple of occasions, he overcame incredibly long shot odds to win. And certainly one of the two most remarkable examples of that was in his fight against George Foreman in October of 1974 in Zaire, a fight that became known as the Rumble in the Jungle. Now, nobody gave Ali a chance in hell of winning that. At the time, Foreman was an undefeated fighter who, at that time, was viewed as much more menacing than even Mike Tyson was at his prime. Ali, of course, by that point, most people thought he'd been washed up. He'd already lost a couple of fights. He won that fight, or we wouldn't be having this, I wouldn't be telling the story. What I want to do is spend a second explaining the difference between his objective, strategy, and tactics. Now, most people understand the objective. His objective was to win. Most people understand the tactics. If I said the word rope-a-dope, how many of you would know what I was talking about? Some of you would. So it's a rope-a-dope is when you lay on the ropes, which is something you should never, ever do in boxing, and let the other guy hit you. Doesn't sound like a good idea. But you see, that's a tactic. The strategy that Ali had was actually very clever. There was two things. His strategy was two-pronged. The first was he was going to tire out George Foreman. And the second piece of his strategy was he was going to humiliate and frustrate him. And if you could humiliate and frustrate a bully, which is what Foreman was, and make him tired, you could win. Everything Ali did after that was just tactics to exact that. And the two most important aspects of that were laying on the ropes, which just allowed Foreman to punch nonstop. And secondly, he did something that a boxer almost never does, which is he led with a straight right hand. So in boxing, your left foot is forward, but if you punch with the right hand, it's a much longer distance. A professional boxer should never be hit with a straight right hand. And yet, he hit Foreman repeatedly with straight right hands, which frustrated him to no end. So, using the brain damage of boxing as the backdrop to this story, let's talk about longevity, beginning with the objective. So, I think it's easiest to explain this graphically. So, the longevity function can, I think, be simplified into two components, or two vectors. The first is lifespan. The second is health span. And I would represent them this way. Lifespan would be like your time variable, and health span here on the y-axis. Now this axis sort of makes sense. I think this is intuitively obvious. Obviously, your lifespan ceases when you are no longer alive, so it's a binary issue. But this health span is sort of a sliding component. Now, I think everybody sort of intuitively understands what health span means. It's obviously some representation of quality of life. But I think it is helpful to come up with some definition for it, and I will not represent that this is a universally or globally accepted definition. It is simply my definition, which is to say that it could be easily challenged, but it provides a helpful framework for the way I think about this clinically. So the way I think about it, there are four pieces to health span. Now, the first two really seem to matter with age. The second two probably do to some extent, but not in as much of a physiologic way as the first two. So the first one is the mind, which for at the risk of sounding a little too touchy-feely, what I really mean by that is cognition. So let's really put in parentheses cognition. And what do I mean by cognition? There are really three elements that go into cognition that we can measure objectively and presumably track over time. So the first is executive function. The second is processing speed. And the third is short-term memory. Now, I suspect everybody in this room knows what each of those are, but you may also or may not be aware that these are sort of some of the things that tend to go away in neurodegenerative disease. You know, it typically starts with a reduction in short-term memory. I think everybody understands what that means, your ability to recall something after a really short time. Processing speed, of course, I think most people acknowledge that, yeah, that kind of gets a little, your CPU, your ability to do a calculation or look at data and make an inference quickly, that tends to slow over time. But I think for most people, executive function is the thing that they hold most dear. And obviously, that's the thing that when it really goes away in later stages of dementia becomes an enormous source of morbidity. The second component of health span is the body. And again, as I alluded to earlier, this isn't really about performance. So it's not how fast you can run the 100-yard dash or how many pull-ups you can do. It's going to be more a function of three other sort of features. The first is the maintenance of muscle mass. And I'm going to hope to convince you by the end of this talk that muscle mass is important whether you're young, old, male, female, think you're an athlete, don't think you're an athlete, it doesn't matter. Muscle mass matters for many reasons, both structural and biochemical. The second element is functional movement. So functional movement, which I differentiate from movement that's not necessarily functional. So not to sort of diminish in any way or say, hey, it's not cool to be able to do the splits. That's not a particularly functional movement. So yes, it's great if you can do yoga and you can do all these great things, but I'm much more interested as a clinician in can you hip hinge correctly? So a hip hinge is, if you drop this piece of chalk, do you have to kind of awkwardly pick it up, or can you squat perfectly and pick it up without any tension, with all the movement in your thoracic spine, nothing in your lumbar spine, that sort of thing. And believe it or not, any of you that have children, if you look at a 2-year-old and they pick something up, they always pick it up just like that. They have perfectly flexible hips. And once a kid gets into grade school, that actually ceases to be automatic, because once you spend a lot of time sitting, these muscles get very tight, these muscles get very weak, and all of a sudden the hip hinge goes away. And so, I would say that I could attribute 80% of the physical morbidity I see that's skeletal in nature to people's inability to hip hinge correctly, because from that everything else flows, in addition to a couple of common muscle imbalances. The third component here is freedom from pain. If any of you have ever been injured chronically, I certainly have been and spent a year of my life in unbearable pain, you realize that most nothing else in life matters if you are actually in physical pain. And unfortunately, as we age, so too do our chronic injuries. And therefore, I consider this sort of the third element of sort of physical health. The other two things, which again don't clearly associate with age as these do, are methods to enhance distress tolerance. So distress tolerance is a set of tools that you have at your disposal to cope with pain that is either physical or emotional, that is either chronic or acute in nature. So that can be anything from you're stuck in traffic all the time because you live in Boston and it's annoying. That's a source of kind of acute emotional pain. And so, there's some people for whom that just doesn't bother them, and there's others for whom that's a great source of distress. And then at the other end of the spectrum, it can be something much more significant. But people have vastly different capacities to cope with distress. And there are some people who have very little distress tolerance and everything just annoys them. And there are others that have an enormous buffer of distress tolerance. And those same insults become much less distressful. So the question is, do you have a bigger buffer? And then the final thing here is sense of purpose and social support. Now, I'm not going to talk a whole heck of a lot about these today, but I do think it's important to just show you the whole picture, which is, in my experience clinically, it is very difficult for someone to have a great quality life if they are not doing well on these metrics. Is it impossible? Absolutely not. Stephen Hawking doesn't have a whole heck of a lot here, but I don't know him, but it's quite possible he's entirely satisfied. So again, it's not an absolute, but it's a way to think about this. So what does the longevity curve look like? So for the average person in this country, it looks about like this. At about the age of 80, it's going to cross there. And it looks about like that. So what are the features of this curve that we want to change? Again, speaking about what is the objective is to change 3 features of this curve. So first, let's look at a couple of its characteristics. So sort of peaks around 40. You hit about 50% of peak, and by the way, from a graphical perspective, I'm mostly referring to these two, right? The mind-body. And then you're going to get the last 50% decline in about the last decade. And I think any of you who have watched grandparents get old or watched other people get old, I think you'll appreciate that at this stage of the game, df by dt is actually quite small. The rate of change here, the decline, is relatively easy to miss year on year on year. Whereas here, it's actually quite precipitous, right? So here, df by dt is actually quite great. And an anecdote is one of my patients is very close friends with Warren Buffett. And he mentioned to me 2 things that struck me. The first is he sees Warren maybe every 6 months. And he said, it's amazing how over the previous year, 2 years of seeing him, that 6 months is more than enough to notice a significant decline in his physical health. The second thing, which I found really interesting, which is just sort of a thought experiment, is he said that, Warren doesn't speak about anything other than health anymore privately, right? So, I mean, obviously, there's lots for Warren to talk about, but really time is the most important thing. And it actually illustrates a point that I would challenge you all to consider, right? Which is, I would be willing to bet that not one of you, if you were offered every dollar of his fortune, would trade places with him right now. And the reason, and you would all intuitively say no, I think, because you realize that time matters more than money. And I would also bet, by the way, that he would be willing to be 20 years old again if he was broke. So never discount this idea of time and what a precious commodity it is. So here are the 3 things of this curve we want to fix. So let's draw kind of the new curve starting about here. So this curve has 3 things about it that now become the objective of longevity. The first is we want to drive more lifespan. Now, a lot of people don't initially care that much about this. A lot of people, I think, and understandably say, look, I just want to live better. I don't care if I live any longer. And that's fine. My view is you can have both. And time is optionality. So nothing I'm going to talk about today fits in the category of what I describe as step function improvements in human longevity. This is all a very incremental, piecemeal strategy to reverse engineering this. But every additional year you buy here does potentially open up the door for some of these step function changes. Can you reprogram progenitor cells? Can you selectively turn off senescent cells? Will perfectly selective rapalogs come along? These sorts of things. The second thing, in addition to actually extending lifespan, is delaying the rate of decline of health span, so slowing the fall. The third thing is compressing the period of morbidity. Again, this becomes a bit of a theoretical exercise. In an ideal world, I'm sure all of us would agree there could be nothing better than having a heart attack in your sleep. Whether it's exactly like that or not, I'm not sure, but I think we would also agree that the current system, which unfortunately is sort of a symptom of what's going on in America is we exert and spend an unbelievable sum of money and put an unbelievable amount of effort into basically just extending chronic disease. So that's part one of the talk. That is the objective. We want to increase the number of years we are alive. We want to delay the rate of decline, and we want to compress the period of morbidity. Okay, so with that, I'm going to mention what the tactics are, because time permitting, we can certainly talk about them. I'm guessing that's what most people want to hear about, and as you can guess, I never like to talk about it. But what we're going to talk about is the strategy, and then presumably get there. So if this is the objective, the tactics are what you eat, how you exercise, how you sleep, how you manage distress, what drugs you take, what supplements you take, what hormones you take, and your ability to learn and unlearn behaviors. So how do you stop doing harmful behaviors? Those are the only 8 things that I think of that you can pull levers on to make that happen. The reason we're not going to go and talk about what to eat and how to exercise and all those things, unless we get the time to do so, is because there is no way of tying that to that without what I hope to explain to you and convince you of is a reasonable strategic lattice or framework through which to think about it. So the question is why? Why do I need to even have this part of the discussion? If this were a talk on treatment of patients with HIV, I wouldn't really have to get into the strategy. I'd say there's a condition where the HIV virus attacks the CD4 cell, and in time you don't have enough CD4 cells. You know, once they fall below a certain level, you have AIDS and you will succumb to an opportunistic infection. So the objective is to either prevent the transmission of HIV and or prevent the progression to AIDS, and then we'd go straight to the tactics discussion, which would be this cocktail, this cocktail, this drug, this drug. It's basically some combination of highly active antiretroviral therapy. No strategy needed. Why? Okay, same thing is true. Person comes into an ER with chest pain, and the blood tests show that they're in the midst of having an active heart attack, and their blood pressure becomes unstable. That's the problem. What's the objective? The objective is to reverse that condition and prevent the patient from dying. Do we need a strategic discussion on what to do? Nope. Any cardiologist knows the answer to that question. There's no thinking involved. Go straight to the cath lab and you know what you need to do. Why do we again get to skip strategy on that example? As you can imagine, I could give you many examples where strategy becomes irrelevant in medicine. But unfortunately, all of those scenarios have something in common, which is the questions that were asked to figure out what the interventions were, what the tactics were amenable to a type of experiment, a type of randomized controlled trial that could be done with humans using hard endpoints to measure outcomes we cared about. So again, whether it's that example, whether it's what's the optimal treatment for peptic ulcer disease, I mean, all of these things are the success stories of medicine because they fit these criteria. There are 5 criteria, which I won't get into, that have to be necessary for the current engine of clinical science to solve problems. Unfortunately, this problem fails on all 5 metrics, right? Can we take 100,000 children, randomize them to multiple different lifestyle intervention groups and follow them for the duration of their lives to figure out? No, of course not, right? So I don't even need to walk you through this. I think it's intuitive that we will never get a direct, unambiguous, experimental answer to this question. And it is exactly for that reason that we need a strategy against which we can evaluate every possible indirect piece of evidence. So the strategy has 3 legs. The first is the study of centenarians. So centenarians, of course, are people who live to be 100 or more in the United States. This represents about 0.4% of the population. And what do we know about them? So we know a lot about them, but I'm going to sort of extract things that might not be the most obvious things you'd think of. So let's start with the obvious. There's a saying in longevity that the single most important thing you should do to live longer is choose the right parents. And of course, the implication is that longevity is highly hereditary, which of course it is, right? I think most people know this. If you dig a little deeper into that, what you realize is, in terms of understanding the genetic basis for longevity, on average, centenarians are no more likely to do or engage in any healthy behavior than non-centenarians. In fact, a number of studies have shown that they're at times more likely to smoke, less likely to exercise, less likely to do the right thing. So rule number one here, or inference number one, is longevity highly under the influence of genes. Well, that's not that interesting for me because I can't change your genes. So what's the next inference? The next inference is, how do they die? So does anybody know how we die, those of us who are not centenarians? So nothing I'm going to say will surprise you, but maybe it's just the numbers that won't be that intuitive. So if you take a group of people who are over the age of 40, who don't smoke and who are not suicidal, and you might say, well, Peter, that's a lot of conditions, but it's really not that many conditions, right? Because what I'm basically talking about is people over 40 who are interested in living longer, which generally means they don't smoke and they're not suicidal. If you limit the analysis to that subset of the population, about 80% are going to die from what we just sort of internally refer to as the four horsemen of death, which are cardiovascular disease and cerebrovascular disease, which is far and away number one, cancer, neurodegenerative disease, which of course Alzheimer's disease is the most prevalent within that bucket, but there are many others, and accidental death. Accidental death, of course, can be divided many more ways, but 80% of accidental deaths fit into three categories. Number one is automotive. Number two is accidental poisoning. And by accidental poisoning, it sounds crazy, right? No, meaning like, you took too much Tylenol, but not because you're trying to kill yourself sort of thing, or you drank too much, but not because you meant to. And then the third one, of course, is falling, which for most people in this room, probably completely irrelevant. Most of us in this room, our greatest risk of accidental death is automotive by far. But as you get older, once you're into the 8th decade of life, falling becomes an enormous cause of mortality. It might actually be the 4th or 5th leading cause of death. So if this is the way that kind of quote unquote the average person dies, the next question is, how do centenarians die? Because if the answer is centenarians all die here, I would feel a lot less confident about my inferences. Because it would be like, well, they've got some magic genes, their genes protect them forever, and it's just a matter of time until they, get hit by a bus. But that turns out to not be true. In fact, JAMA published these data about a year ago, which was a look back at mortality of centenarians across some of the largest series. And it found that centenarians kind of die the same way, with a couple of exceptions. Heart disease goes up quite a bit. Cancer goes down. Neurodegeneration is about the same. And in here you stick in pneumonia. But not much of a change. Now I could, if this was a discussion on lipidology, I would tell you why this is the case or offer my explanation as to why it's the case, but it's not really relevant. The point to take away from this is centenarians are not immune to death. The difference is they get these chronic conditions later than non-centenarians. And so work out of Albert Einstein, which there's a group there that studies this problem significantly. They found that on average, centenarians are not even acquiring the first clinical sign of these diseases until they are between 80 and 98 years old. Whereas the rest of us schleps are getting the early clinical manifestations of these diseases about 20 years sooner. So this actually becomes, to me, the most important insight from the centenarians, which is the key to living longer is delaying the onset of chronic disease. Now, that sounds so obvious that it's not interesting, but I really want to repeat it. Disease is an integral. Disease is compounding. Not every disease compounds in the same way, certainly. But just because somebody has a heart attack at the age of 69 does not mean that they weren't riddled with disease at the age of 68. They absolutely assuredly were. The question is, what could have been done had they started early enough to slow the rate of progression of that disease such that it didn't become clinically evident at the age of 69? So the second insight here then is to live longer is the mathematical equivalent of delaying chronic disease. The third insight from the centenarians, which is probably the part that would be most interesting to this group, is what are those genes? So we talked about how it seems largely under a genetic control, but the question is, what are those genes? And it turns out this has also been studied, and there are about a dozen or so genes that tend to cluster in people who live longer. Now, I think for the purpose of time, it's not worth going into what every one of those genes are, but I think I'll use a few of them as examples. So, what are some of the common genetic differences we see in exceptionally long-lived people? They tend to have hypoactive ApoC3. They tend to have hypoactive PCSK9. They tend to have ApoE2 over 3 or 4. They tend to have less GHR. They tend to have lower IGF-1. And if you list all of these things out, with the exception, I think, of one of the thyroid mutations, is the only one that I don't really see a clear relationship to chronic disease for, every one of these gets tied back to one of those. So, in other words, what's really interesting is think about what is the phenotype of someone that has this genotype, right? The phenotype is what's interesting because maybe there's a chance we can mimic the phenotype even if we don't have the gene. So those with low ApoC3 or hypoactive ApoC3, it's never that you're absent these genes, they tend to have lower triglycerides and lower ApoB. ApoB, of course, being sort of one of the three most important things that you would want to understand to assess cardiovascular disease risk. People with hypoactive PCSK9 have much more LDL receptor on their liver. They clear ApoB-bearing particles out of circulation with an alarming degree of precision. These are actually, this family was only discovered in 2006 of individuals. ApoE 2 versus 3 versus 4, apolipoprotein E plays an important role both in peripheral metabolism of cholesterol, but also in central metabolism of cholesterol. And the ApoE4 genotype, which is actually the one that we all came from, so this actually turns out to provide pretty remarkable protection for parasitic infection, which served its purpose, hundreds of thousands of years ago. But we then evolved down this chain, and today those with an ApoE2 have a more than 20-fold reduction in the risk of Alzheimer's from this population. So this is the wild type today. These people are at a much higher risk. These people are at a lower risk. Those with low or slightly defective GHR and low IGF seem to have protection from cancer. So this basically is the first piece of the story, which is if you want to live longer, you delay the onset of chronic disease. The people who naturally do this got really lucky. They acquired a set of genes that gave them a phenotype that delayed the onset of these. So from a clinical perspective, what I take away from all of this is we have to know everything about these diseases. I'll use heart disease as one example to illustrate the difference between sort of taking an overly simplistic view versus perhaps a more nuanced view. If I said to the average person, average physician, what are the most important steps to reduce the risk of heart disease? They would probably say, don't smoke, control blood pressure, and keep your cholesterol low. And I will tell you that directionally that is absolutely correct. But the problem with that is at the margin, it's actually missing a very important point. Now, there's no doubt about it that smoking and blood pressure control are important. So important that they're no-brainers. I almost take them off the table. But to say that keeping cholesterol low is important, while most of us have been led to believe that, actually misses the point. Atherosclerosis is not a cholesterol disorder, it's a lipoprotein inflammatory disorder. In fact, really the three most important things that we ought to be thinking about for cardiovascular disease are how to control lipoproteins, inflammation, and endothelial function. Because if you don't have endothelial dysfunction and the lipoproteins don't get to where they need to go, and you don't have the inflammatory response that creates this chronic condition, you don't actually have heart disease. And so when we focus on cholesterol instead of lipoproteins, we make an enormous mistake. And when we ignore inflammation and endothelial function, we're also making a mistake. There's actually unpublished data that are going to be, I think, very interesting because this is now starting to become a target of clinical therapy. So for example, a trial that I think is only out in abstract form looked at very, very low doses of methotrexate in high-risk cardiac patients. No other change, so both groups have the exact same lipid control, but the group that had a low dose of methotrexate, which is an immune suppressant, actually had reduced cardiac mortality. So again, there's a lot more nuance to these diseases sometimes than meets the eye. I think Alzheimer's disease would be another example. Unfortunately today, the conventional view of Alzheimer's disease is that it's not a preventable disease and that there's sort of a final, everybody kind of has the same disease where they accumulate beta amyloid and they get this condition. The anecdote I would share with you is that one of the people that we collaborate with is a neurologist at Cornell. When he writes grants to NIH, he is not permitted to use the word prevention anywhere in the grant. So he cannot get money from NIH to do anything in terms of Alzheimer's prevention. He has developed a system at Cornell that's become so good at managing patients in early cognitive decline that the NIH asked if they could bring it into what's called the NIH toolkit for Alzheimer's disease, but their only condition was he had to remove the term Cornell Alzheimer's Prevention Clinic from the title. So unfortunately, there is still a view that is that these things can't be prevented. And while I think we could debate the proportion of each of these that's preventative, I don't think anything's 100% preventative, but I would be willing to bet that 1/3 to 1/2 of cases could be prevented. So now on to the second pillar. So the nice thing about centenarians is that they're humans. The not nice thing about centenarians is we don't get to actually do experiments. So everything I just said to you is observational in nature. Now, yes, so you can do some Mendelian randomization and you can sort of get confidence on a few of these things. I think the ApoE4 is far enough, it's almost impossible for that not to be causal given the size of the hazard ratio. It's sort of like smoking and lung cancer. Once your hazard ratios get into like the double digits, causality is generally a given. But for many of the other things, it's not entirely clear. It's not entirely clear that IGF has a causal relationship to cancer. It certainly seems like it could be, and maybe in certain cancers more than others, but it's complicated. In fact, to really make these inferences, you have to be able to do an experiment, and to do an experiment, you have to give something up. So in order to get something, you got to give something up. So in order to get the luxury of being able to actually do science, you got to give up the species of interest. So the second sort of pillar in my mind of how I think about this problem is the non-human literature. Now, there are many people in this room who know infinitely more about this topic than I do. So I certainly won't even, pretend to get into a lengthy discussion about this. But in my own sort of plebe way, I thought, how could you take such an unbelievable volume of information and make heads or tails out of it? And I think I like to simplify sometimes, and that comes with risk. But in this case, the simplification was, let's ask the question, what are the interventions that have been shown in non-humans to nearly uniformly extend life across the broadest selection of evolution? So if you ask the question, from yeast to flies to worms to mammals, are there any interventions that seem to consistently work? The idea being, if this was about 1 billion years here, something that only works here but doesn't work anywhere else just seems less interesting as part of a lattice that we're going to use to evaluate interventions when it comes down to trying to ask the question, can any of this be applied to humans? So again, for the sake of time, I'm just going to go to the punchline. The punchline is there are sort of 3 things that kind of jump out from this body of science. The first is that some combination of CR and DR seems to matter. So I'm guessing everybody in the room knows what that means, but so CR is caloric restriction, DR is dietary restriction. What's the difference? The way we're going to use these is caloric restriction says you are consuming fewer calories than your metabolic rate and activity level would otherwise dictate. So, if an animal would normally need, 200 calories a day, you would maybe put it on 60 or 70% of that, in many cases for its entire life. Dietary restriction, conversely, means you are not in any way restricting calories. The animal can consume food ad libitum, but you are restricting some macronutrient. You might restrict protein, or even something narrower than that, like methionine, one of the amino acids in a protein, or you might restrict sugar, or something else. So my guess is that this is the sort of most obvious answer people would give when you ask the question, what seems universally true across these organisms? But I will say the answer is not entirely obvious, the relationship between these. And sort of the experiment that I find most interesting in this space is actually the largest and probably the most famous of these, which I'm sure some of you are familiar with, which was the rhesus monkeys experiments at the University of Wisconsin and the NIH. And these were a series of experiments that took place over many years, I believe 18 years, 20 years, done sort of in parallel, not really done in parallel, but also not completely independent in that they were obviously somewhat coordinated. The results of this study have been published in different pieces over many years, but it's also produced a great amount of confusion. So in 2009, when the NIH cohort was finally published, which I believe was in Nature, I still remember the headline, which was effectively caloric restriction doesn't work. Because in the NIH cohort, the calorically restricted rhesus monkeys did not have a survival advantage over the ad lib animals. And of course, in the Wisconsin experiment, you actually saw an advantage in all-cause mortality for the UW calorie restricted versus not. But I'm going to explain to you that I actually think the results of these are consistent and point to a relationship for DR. So very quickly, what happened here, and by the way, I don't know if Bob has it up, but Bob one day wrote up a hilarious analysis of this where he took the monkey food diets because you can read in the methods everything that the monkeys were eating in these, and he put it in terms of standard American diet food. So he was like, okay, the controls here were eating this many Big Macs and this many fries and this many milkshakes, and these guys were doing this. And so it makes it very clear what was going on. In a nutshell, it was the following. The NIH monkeys were consuming a diet that somewhat resembled their normal diet. Now, it didn't because it was high in a bunch of weird stuff, but it was sort of an attempt at real monkey food. And importantly, it was very low in sucrose. It was only 3% sucrose. So not that, because obviously wild-type monkeys wouldn't have any sucrose in their diet. And in this experiment, the controls ate ad lib, and there's another nuance to this I won't get into, and the treatment group ate, I believe, 60% of that. And if you look at the Kaplan-Meier curves, the calorie-restricted monkeys did not live longer. And in fact, some of the mortality benefits that they had with certain chronic diseases were offset by other types of conditions. So non-chronic disease death. In the Wisconsin experiment, it was something different. They used a liquid formula to feed the monkeys. And it turned out, and I actually spoke to one of the people who was involved in that study, and he kind of explained to me how the history of this went. They couldn't get the monkeys to drink this formula. It just didn't taste that good. It was kind of gross. So the only way they could get the monkeys to drink it was they had to put a lot of sucrose in it. So the formula was 25% sucrose. So, I mean, that's like shockingly sweet. But now the monkeys would drink it. So in the Wisconsin experiment, you had, you know, sort of absolute complete crap food versus, you know, 70%. So 100% crap versus 70% crap. And lo and behold, there was a survival advantage here. These Kaplan-Meier curves spread. And so my interpretation of this is not that calorie restriction didn't work. It's that calorie restriction didn't seem to matter as much when the diet wasn't so bad. But the worse the diet, the more benefit you might get from actually eating less of that diet. I mean, it seems intuitive, but it really speaks to a broader question to which I don't think we know the answer, which is, what type of dietary restriction could produce similar benefits to the best form of caloric restriction, which in and of itself is a question we don't know the answer to. I mean, as those of you who in this room maybe follow this stuff, you know, when we talk about caloric restriction, we also tend to speak about caloric restriction mimicry. So how do you mimic CR? Well, you can mimic it by intermittently fasting on a daily basis. Or you could intermittently fast on a monthly basis, or something else. So we'll probably come back to this a bit more later, but the point here is there's something going on with CR and DR that matters, and that which is number 2 will start to shed light on that. So number 2 is, in all of the drugs that have ever been tested across all of these different organisms, only one has demonstrated consistently an advantage in survival. Now, there's probably no one in this room who knows what that drug is. So, no, this is a question that in any other audience, no one knows the answer. In this audience, everybody knows the answer. So there's something about rapamycin that lands here, which is rapamycin extends life across this spectrum. And, of course, large part of what we're here today to talk about is longevity, and you know, you could argue that the target, that which rapamycin works on, this protein called TOR, probably sits in the center of a part of you know, the organism that plays a very important role in how it not only responds to nutrients and stress, but basically growth and non-growth. So something about rapamycin, and I just put in parentheses here, mTOR also seems to matter. And now you can maybe even get a sense of why this thing's here, because there are some similarities here. You see, caloric restriction and dietary restriction interfere with nutrient sensing. So this is a way you interfere with nutrient sensing with a small molecule. This is a way you influence nutrient sensing with macromolecules. The effects can be quite different, but there's an overlap. I'm not going to spend much more time talking about rapamycin because that would be like, you know, there's an expression like teaching the Pope to, I don't know what, teaching the Pope to pray or something, I don't know. But I'm not going to do it. Okay, so what's the third insight that I think comes from the non-human literature? It's basically the genetic insights that marry up to some of our centenarian stuff. So in humans, you can't really do genetic experiments, but it turns out you can do lots of genetic experiments in animals. So potentially the most famous of these are the DAF2 mutants in C. elegans, which, just quickly I'll explain for those who might not be familiar with it. So C. elegans is a worm that you know, actually has a remarkably similar longevity curve to humans in terms of the shape. It lives on average about 18 days, and it spends about half that time perfect, and then about half that time sort of in decline. And it turns out that if you completely shut off DAF2, well, the animal doesn't survive. But if you just attenuate it slightly, and there's many different degrees to this, but if you hit it in the right spot, you can get this organism to live 2.5 times longer. And at least one experiment I saw, you actually changed its mortality curve from this to this. I mean, it just like was perfect until the day it died. And it lived a little over twice as long. So why is that interesting? Well, we don't have DAF2 genes, but we do have IGF-1 genes. And it turns out that the DAF2 gene codes for a receptor that in the worm does something very similar to what our insulin and IGF receptors do in us. And so I'll just put here genetic insights. There are many of them, and they become a way for us to start thinking causally about some of the genes and phenotypes we see in the human centenarians. So in summary, the second pillar of the strategy says, what are the consistent and preserved findings when it comes to extending the life of organisms across about 1 billion years? We use that as such a high bar because we can be more confident that if something is conserved across such a long period of evolution, it matters. Now, I am sure there are many other things that we could be adding to this list if we would restrict ourselves to narrower subsets of this timeline. But I felt that given that everything that we're talking about here is to make a leap of faith in humans, it's better to err on the side of maybe being a little bit more conservative in our thinking of, what really matters. So the third and final pillar of the strategic, sort of lattice or framework is the most confusing. And it's the molecular insights. So when it comes to the centenarians, we're basically doing epidemiology and ecology. The advantage we have is we get to look at the species of interest. The disadvantage we have is we don't get to do any experiments. When we do experiments in animals, we get to control variables and we get to infer cause and effect. We just don't get to do it in humans. But both of these things, in particular, that second point, lead to a lot of the type of work that's done right here, which is from that understanding of CR and DR and rapamycin comes a whole series of insights. But the most important of these would be the role of nutrient sensing, autophagy, senescence, inflammation, and there are others. This list goes on and on and on. But I think for the purpose of time, what I really want to do, because I know that people do want to have a little bit of a discussion about the tactics, and I can sort of sense everybody's like, all right, we got this thing. But the nutrient sensing thing, right? I mean, I think, again, I don't need to say much more about it in this audience, but we didn't evolve in the environment in which we currently live, right? This is, in terms of our genetic, I think I did the analysis once in terms of food abundance. I think it's less than 0.1% of our genetic existence has been exposed to this nutrient density. I mean, we've just never had such abundant nutrients. And therefore, it would be, I think, glib to assume we have evolved to be perfectly optimized in this environment. And so therefore, there's something potentially about the withdrawal of nutrients at points in time that seems to be beneficial. Autophagy, of course, is a very exciting discussion today. Not only are there people in this very room who work very closely on this, but of course the Nobel Prize was awarded last year for the discovery of the sort of genetic regulation of this. And we know today, of course, that autophagy, which is literally the ability of cells in the body to sort of auto-digest others, plays a very important role. And by the way, probably has a pretty important overlap with this, though not entirely. Senescence is kind of something that I think is probably still not quite ready for prime time. Certainly not clear in humans what the implication is, but in animal models it's pretty interesting, which is that there are cells in the body that are simply poisoning, for lack of a better word, other cells through cytokines and inflammation to basically advance an aging phenotype. And in animal models, select animal models, when you knock these cells out, you reverse the aged phenotype. Now, like autophagy, these things always tend, and like nutrient sensing pathways for that matter, these things tend to be two-edged swords. So you can certainly make the case that without any senescence, cancer has, a cancer cell has an advantage over a non-cancer cell. And then lastly, inflammation, which again is one of those things that I think doesn't quite get enough attention, but certainly if you come at this through the clinical lens of cardiovascular disease, which is really the disease I probably think the most about, because it's statistically when you talk about cerebrovascular and cardiovascular disease, it's the one that's going to kill the most people. It's a highly inflammatory disease. And when you think of all of the things, whether it be in our diet or in our environment, that can impact inflammation, the more we understand the science of this, the more we understand potentially what we can do to modulate it. So with that, let's now go and talk a little bit about the tactics, and then we'll get to Q&A now. It's at 3 o'clock now, so maybe I'll just take a moment. I know this was probably only booked for like an hour. If anybody wants to leave, you're not hurting my feelings, that's for sure. And if not, hopefully I'll make it interesting enough that you'll be glad you stayed. So the third piece of this, so we have an objective. We discussed our strategy. Now, how do you put the strategy into place? Well, you have tactics. The what you do. So nutritional biochemistry, exercise physiology, sleep physiology, techniques for distress tolerance. And I think from the standpoint of time, I'm not even going to get into the other four. I don't think I'm going to get into endocrine, supplements, drugs, and harmful behaviors. Obviously, if people have any questions about that stuff, I'll be happy to address it. But what I do want to do is kind of give people maybe the most succinct punchline I can provide. So from a nutritional standpoint, I am about to give you what I consider the most helpful dietary advice I could ever give somebody that is pretty much useless to implement without a better understanding. But this is the answer. The answer is you should optimize your nutrition such that you consume your carbohydrate consumption is such that your average glucose is low. I define low, by the way, as 85 milligrams per deciliter. And again, if you ask me to tell you why it's 85 and not 88 versus 90, 91, or 82, I can't. I'm just telling you, based on empirical work, 85 as an average 24-hour glucose over time is a great number, and a standard deviation of less than 15 milligrams per deciliter. Whoops, I put percent there. And these two conditions will lead to a relatively low AUC, so insulin AUC. So we can't do this outside of a hospital, but in an ideal world, what I'd love to do with every patient is put a central line in them and sample their insulin level every 30 to 60 minutes, and at the end of every day, have the integral function, which would look like this, right? So it's insulin by time, dt, 0 to 24 hours, and that gives you a number. And that number should be minimized. So that's really the objective here, is to min that function. We can't do it. Insulin is far too complicated. You can't measure insulin in a point-of-care device. But we can measure glucose that way, and we can measure glucose continuously, which I like to do. And so we use as a proxy for minimizing the insulin AUC this idea of keeping average blood glucose low and standard deviation low. Why the standard deviation, you may ask? Because the insulin response to these two curves is different. That glucose curve versus this glucose curve will have the same average glucose, but a very different insulin response. And so what we're really looking for is perfect glucose homeostasis. When it comes to protein, so that's what I would call our carbohydrate philosophy. Notice it is entirely agnostic towards whether you're paleo or vegan or I don't care what. I view myself, and I know I get sort of put in a bucket of being like a keto guy or this guy or that guy. I sort of reject all of that stuff out of hand. I find it quite frustrating. Really, you have to be, I think, it's a difficult thing to say because it sounds crazy. You have to be unemotional with respect to food. And as a guy who loves food, that's a hard thing to say. But you just have to sort of, for a moment, just consider food as just a bunch of molecules that impacts enzymes and hormones in your body. You just got to think of it that way. And then you can put all the emotion back into it when it comes time to eat. With protein, the approach is going to be a barely positive nitrogen balance. So nitrogen balance, the way we would measure this clinically in the hospital, which we used to do all the time in patients who are in an ICU, is you actually do a metabolic tent and you collect their urine, and you're basically knowing how much protein and amino acid you put in and how much nitrogen comes out. And for patients who are burn victims, for example, we want to make these people so so anabolic because they're naturally so catabolic that we titrate their amino acid input to make them have such a high positive nitrogen balance. But the problem is, as many of you know, excess amino acids, while we used to think of them as quite metabolically benign, because unlike fat and carbohydrates, you don't really store protein, so it seems like a free meal because the urea just comes out in your urine. It turns out that view that I think was sort of the view 20 years ago probably isn't the case. It might be that excess amino acids, beyond what are necessary to maintain homeostasis or maintain the state of muscular sort of congruence, might actually lead to problems, right? So these amino acids play a very important role in these nutrient sensing pathways, and a number of them in particular may have been already implicated in disease progression. So do we want to be at the other end of the spectrum? Do we want to be in a protein wasted state? No, we don't, because again, I hope to convince you that exercise matters, and if you recall back to what I said about body, maintenance of muscle mass matters. So there's a fine balance between how much protein do you need to maintain muscle mass versus what is too much where it starts to become harmful. For the sake of time, I'm not really going to get into fat, other than to say at a caloric level, it ends up being the balance after this and this are adjusted for. So just as I go back to the Muhammad Ali example, Muhammad Ali had an objective, a strategy, and a tactics. If you put me in the ring and I tried those same tactics, I wouldn't win. So that's why I can't just give you a prescription. I can't say eat this many grams of carbohydrates. What I can say is you eat as many grams of carbohydrates as you can tolerate to do this. And for some people, that's a lot of carbohydrates. And for some people, it's not a lot of carbohydrates. And so this number and this number end up being highly dependent on the individual, on how much they exercise, as I'll explain in a moment, how well they sleep, how well they manage distress. All of these things feed into this, but it effectively becomes a function of fuel partitioning. How well you partition fuel, which is dependent on certain genetic factors like how much lipoprotein lipase you express on muscle cells versus fat cells, and also a number of things that are related to these other interventions. So fat effectively becomes the balance by amount, and then I think some of the literature would give us a point of view on the distribution of those fats. Because again, you think of these through the lens of monounsaturated fats, saturated fats, and polyunsaturated fats. And it's not clear that these are entirely equal, and therefore there's probably some manipulation of those that can allow you to optimize nutrition. With respect to exercise, I think, again, we just put performance aside and we ask the question through the lens of what are the necessary exercises to achieve both our longevity goal, both our lifespan goal and our health span goal. On the lifespan side, what we really think about is the metabolic advantage of exercise. And the most important might be glucose disposal. So anyone here who's in medical school or even just is in a biochemistry class knows that we can put glucose away quickly into only two places, the liver and the muscle. So the liver has a relatively finite capacity for glycogen. And the muscle turns out to have a much more elastic capacity for glycogen. So the larger the muscle, the more insulin sensitive the muscle, the more glucose that it can dispose of. And the goal is to have muscles that are really big sinks for glucose. And the bigger your sink is, and the more efficiently it can take in glucose, with a lower level of insulin, right? So that's a marker of its efficiency, the more of this you can tolerate. And so there was a paper I saw about 2 years ago that actually looked at people who were pre-diabetic, and it took muscle biopsies from them in different areas. And it showed that the single greatest predictor from this for the development of type 2 diabetes was insulin resistance in the muscles of the lower body, which is not really that surprising. I mean, I do OGTTs, oral glucose tolerance tests, on all of my patients, and I do them with frequent sampling and measuring glucose and C-peptide and free fatty acid and insulin over long time periods. And I can tell you that long before a patient is even remotely diabetic, they have elevated insulin, not necessarily at fasting, but the harbinger is elevated insulin in the presence of normal glucose disposal an hour after a glucose challenge. That's a patient who will evade all detection, but who in 5 years is going to start to have an elevated fasting insulin or an elevated or impaired glucose disposal. And eventually they're going to have the bump in the A1C, and eventually they're going to have diabetes. So it's really hard to have diabetes when you have a lot of muscle. And that's part of the reason why. At the other end of the spectrum, we have other components to this, which is the health span side of things, which is obviously maintenance of muscle mass, but also some of these structural benefits. And so I think the other component clinically that's really important here is injury prevention. For example, if you consider lower back injury, so 80% of the population in the United States will experience at least one bout of acute lower back pain in their lifetime. Acute lower back pain is defined as lower back pain that lasts up to 2 weeks. And I won't ask for a show of hands, but I would be surprised if many people in this room, though the average age is quite young, will have experienced that. Well, that's just one example of a type of injury that's quite preventable and yet can lead to a very high amount of morbidity. I'm not just talking about sort of a loss in productivity at work, but a spiral that can lead to I exercise less, I sleep less, or I sleep poorly, and then all of these things sort of unfold. So as a general rule, what I explain to patients is if you don't like exercise, I'm sorry. If you only want to make time to do one type of exercise, it needs to be strength training, and it needs to be quite heavy. I tend to divide this into two categories. If you enjoy heavy hip hinge compound joint movements like deadlifts and squats, great. You learn to do those correctly, and they will serve you indefinitely in life. And that includes if you're 90 years old and you can barely see, you will still get tremendous benefit from squatting, deadlifting, rowing, doing these types of movements. Conversely, people who just don't want to learn that or are intimidated by it, there are other protocols that can sort of approach some of the benefits of those things. For example, a protocol pioneered by a guy named Arthur Jones in the 1970s, which is called a super slow protocol. Others have come and made it much better. Effectively loads you longer, heavier, but with less volume, and produces many of the same effects. It's effectively, you want to be able to get the type 2B muscle fibers activated. So you have type 1, 2A, 2AB, and 2B. And for most people, it's really foreign to have their 2B muscle fibers activated. And that's sort of what we're trying to do in this type of training. For people who like to exercise, I say, great, you're still going to do strength training. The question is, what's the remainder of the time? For me, just because I don't really want to spend that much time exercising anymore, outside of strength training, the only thing I sort of do now is interval training, which is either done on a bike, on a stationary bike, or on a treadmill. But for others, they want to spend more time doing that. The only thing I sort of caution people on here is, it's, I think, becoming pretty clear that there is a risk of over-exercising. James O'Keefe, who's a cardiologist in Kansas City, who's done a lot of work on this, the so-called athlete's heart. We've known for quite a while that really serious athletes have about a 7 to 10x increase in the rate of atrial fibrillation to non-athletes. And that's a bit unusual because we associate atrial fibrillation as a condition of people who are sick. But it turns out that the atrial fibrillation that athletes get looks very different. And it probably has to do with stretching out the atria and the implication that has on the electrical system of the heart. Sleep. I'll talk about it briefly because, frankly, I think it's the most underappreciated, though I think that's changing today. Most people think sleep is kind of, yeah, I'll sleep when I'm dead, or it's not that important. I would only challenge you with the following, which is sleep is one of the most highly conserved behaviors of our species that doesn't seem to go away. And it's actually, if you think about it, you spend about a third of your life sleeping. And if there was a way to out-evolve that trait, I think we would have. And it's interesting that we haven't, given that it takes you out of the game and it can potentially be dangerous. So there's actually some interesting, albeit small, experimental literature on sleep. The first thing that I realized about sleep was after residency, when I realized that after 5 years of averaging probably 3.5 to 4 hours of sleep a night, two things immediately changed once I started sleeping 6 hours a night, which, by the way, still wasn't perfect, but that was sort of the next evolution. The first thing is my testosterone tripled. So when I finished residency, my testosterone was 220, my total testosterone, which is sort of the 5th percentile is 350. So I was, like the 2nd percentile of testosterone. I was like a 13-year-old girl or something. And so why did that go up more than 6 times? It was actually probably about 7 times it increased. And part of that probably has to do with certain things that the brain is able to do during slow wave sleep. So sleep is divided into alpha wave, delta wave, theta wave, and then you have a couple of these spindles that show up on EEG. But in particular, this delta wave or slow wave sleep, it seems that may be where our pituitary gland actually puts out FSH and LH, or the hormones that tell the body to make testosterone. The second thing I noticed when I started sleeping more was my memory became better. I was able to consolidate memory in a way that I wasn't able to earlier. And I also realized going back that the hippocampus is quite sensitive to sleep disturbances. And the hippocampus, of course, is where we at least begin the consolidation of memory. And so anything that interrupts that is problematic. But it wasn't until 4 years ago that I saw the real benefit of sleep experimentally. An experiment that was done at the University of Chicago took a very small number of subjects, but the experiment was so well done that I'm inclined to think that it would be reproducible, though to my knowledge it hasn't been reproduced. It took a group of healthy volunteers and did euglycemic insulin clamps on them. So that's the gold standard for measuring glucose disposal and insulin resistance. It's a research-only test that's very involved. It's the one David was alluding to that I almost died having done to me because my glucose got so low. And so they did this test on people which measures their insulin sensitivity. And then for 14 days, these subjects were permitted to only sleep 4 hours a night. And then they were retested on the euglycemic clamp at the end of 2 weeks. By the way, there had been no other change in how much they were permitted to eat or anything during that intervention. And their euglycemic clamps deteriorated by 50%. So sleep deprivation directly, though the mechanism is unclear, exacerbated effective glucose disposal. And I see this now clinically much more. It's probably always been there, but I think I'm just more cognizant of how much you can improve glucose disposal by correcting sleep. And what's not clear yet is it just the total amount of sleep? Is it particular to a certain phase of sleep? I don't think we know the answer to that yet. I think for the sake of time, I'm even going to skip distress tolerance and just leave it at as you can probably tell, some of these interventions have really simple prescriptions. In 10 minutes, I can probably tell you 80% of what you would need to know about sleep. Conversely, some of these are really complicated. And I think none are more complicated than certainly of the ones I've spoken about than nutrition. If for no other reason than, if there are 80 people in this room, there might be 70 different ways to feed the 80 of you to get optimal results. In other words, it's very difficult to look at an individual, even look at their blood work once you have it, and know what to do. It just becomes empirical, and it just requires feedback and measuring certain things as you go along the way.